Welcome along to your weekly SETI seminar for today, 24th of March. Today we have Bob Pappalardo joining us from JPL. Bob got his undergraduate degree at Cornell and then did a postdoc at Brown University and, a PhD at ASU, followed by a postdoc at Brown University and and then moved to CU after to be an assistant professor at CU for 2000 to 2006, when he moved to JPL to shepherd through the flagship to the outer planets, which he's going to talk to us about today. Bob's background is in the Galilean moons. He's written extensively on the possibility of an ocean beneath the icy crust of Europa, and also for the possibility of convection within the icy shell of Europa. Recently he's been looking at Enceladus while Cassini is in the Saturn system. Today he's going to talk to us about a mission that hopefully isn't too far off, and that's the Europa Jupiter System Mission, which he is now the shall I say, the guardian angel for, at least at this stage. Okay, so if you'll all join me in welcoming Bob.
Thank you. Thank you. I appreciate the great turnout, and it's just a pleasure to be here to talk with you today and to get you up to speed on the Europa Jupiter System Mission, a mission which is in development and which is an international mission, where the plan is that NASA do a Europa Orbiter and ESA does a Ganymede Orbiter. Both explore the Jupiter system together for 2 to 2.5 years in orbit around Jupiter, and each goes around its respective moon, with the combined overall goals of understanding habitability and understanding processes at icy satellites and in the Jupiter system. So I should say that this international group is, as we speak, in the process of taking its independently developed science traceability matrices and combining them into one in the spirit of one mission with 3 overall goals: Europa, Ganymede, and Jupiter system. What I'm going to show you is still a little more of the split personality prior to this latest work to fold these together. So I'm going to concentrate more on the Jupiter Europa Orbiter and the related science. So of course we just passed the 400th anniversary of the discovery of the Galilean satellites, and we've sure learned a lot in 400 years, much of it attributed to the Galileo spacecraft, of course, which made many close flybys of the Galilean satellites, especially Europa, in the extended mission of Galileo. Of course, Europa standing out as rock-like density of 3, yet an icy surface. So it's a rocky moon on the inside, but an icy satellite on the outside. Very bizarre geology. If you look at the surface of Europa, it strikes you as different right away in having these linear features crisscrossing the surface, areas of modeled terrain, and very few visible impact craters. The few large craters we see, as Kevin Zomley's work largely has shown, makes the best estimate of the surface age something like 60 million years. This is what the ridged plains look like close up, crisscrossed with ridges and grooves, ridges generally traveling across the surface in pairs and not fully understood. We'll look more carefully at those in a second. And the chaotic terrain, the modeled terrain, Areas that look a little more like hamburger here, something has come out and destroyed pre-existing ridges and replaced that surface with this hummocky terrain. Very few craters. This probably a secondary from a larger impact. So here's what the ridge plains look like close up again, colorized with lower resolution data, zooming in on one of the ridges about 2 kilometers across. Excuse the stuttering of the movie there. How these ridges formed is debated. I argue for a model where they are largely intrusive, where we see older features looking like they are warped upward as the ridge has formed by intrusion, something coming up from below, warm ice presumably. But it's very debated as to whether the ridge plumbing is literally connected to an ocean or more related simply to tidal effects of an icy shell above an ocean. So in general, intrusion or extrusion of water or solid state ice sort of covers the bases as how these ridges might form. And looking at the chaotic terrain closer up, this too is lower resolution Galileo data. This is about 180 or so meters per pixel. And as we zoom in, we'll see that this darkly colored region starts to look more familiar to you as we zoom into some of the higher res data where those blocks are more visible. Blocks which appeared to have translated and rotated in a hummocky matrix. They used to connect up, and some, like this one, have literally split apart and rotated and pulled apart. Again, debate as to whether this hummocky matrix is suggesting literal melting or if it's related to solid state ice that has flowed. Zooming now into some of the highest resolution data from Galileo of Europa, 10 meters per pixel, where you can see these cliff-like faces of ice and then shallower faces, implying active mass wasting is going on this relatively recent surface. Oh, again, excuse the stuttering of the movie as my computer tries to keep up. These troughs about the size of an interstate highway. Here's one of the blocks and an old ridge, not looking very happy. Something has presumably heated the pre-existing surface from below, whether that is caused melting or partial melting potentially related to diapirs that are moving upward to the surface, blobs of warm ice essentially moving upward to the surface and partially melting ice is one idea. So is there liquid water below this surface today? Is this region active today? Given that the surface age is on the average about 60 million years, in just 1% of the age of the solar system, Europa probably hasn't shut down and is probably still active today. This is an idealized model of what Europa's shell might look like, with the idea of these warm ice diapirs that warp up domes and create spots on the surface. Areas where diapirs are concentrated, perhaps tidal heating concentrated there, might form regions of chaos above them. There are dark bands that appear to have pulled apart that can be reconstructed with no gaps or overlap if you push them back together. There are multi-ring structures that appear to have punched all the way through the ice shell, suggesting that the ice shell is something like 20 kilometers thick. But there's debate over that. Some would argue that the ice shell is only a few kilometers thick and that there are other ways of making these features in a thinner ice model of how Europa works. We know from gravity data that Europa is probably differentiated, again, mostly a rocky body, but then about 100 kilometers worth of H2O. And is some or most of that H2O layer liquid? Well, again, impact craters and the inference that Europa's ice shell is probably convecting suggests that the ice and thermal modeling suggests that the ice shell is something like 20 kilometers thick, but there's room in that estimate. It might be thinner or thicker. We don't know how much heat is coming from below, and that's an uncertainty in the modeling. That is, how much tidal heating is concentrated in Europa's ice shell as it's heated, as it orbits around Jupiter, is tidally heated. Is there significant tidal heating in the mantle? If there is, that's of significant interest to astrobiology because that's a source of reductance. There's potentially a source of oxidants at the surface due to irradiation of the surface in the Jovian environment. And so if material from the surface, oxidants can get into the ocean, if there's significant tidal heating in the mantle and reductants get into the ocean, that could be a nice place for life. Europa is bathed in this radiation environment of Jupiter, and Europa creates its own induced magnetic field in response to Jupiter's magnetic field. So as Galileo, the spacecraft flew by Europa, it noted a magnetic field that seemed to counter the action of Jupiter's magnetic field. It creates an induced magnetic field, and that is the best evidence we have today for an ocean within Europa. But of course, we want to measure, we want to determine, we want to confirm that that ocean is there using gravity and altimetry, and we want to characterize that ocean. How salty is it? How thick is it? So that's some of the motivation, and we'll touch on more as we go forward, for the Europa Jupiter System Mission, which I'm told we're coming out of the bilateral, which is going on this week, potentially with a name for this mission, so soon we may have a real name. So again, as I mentioned, NASA and ESA having essentially shared mission leadership here. Independently launched and operated orbiters, NASA-led Europa Orbiter and ESA-led Ganymede Orbiter. So a little bit of an alphabet soup here, but when you see JEO, Europa, JGO for Ganymede, complementary science and payloads, where the Europa Orbiter is here schematically going to concentrate on Europa, but also make flybys of Io. The Ganymede Orbiter concentrates on Ganymede, but will also make a significant number of flybys of Callisto. Now, the Europa Orbiter also makes some Callisto flybys and Ganymede flybys, but the Ganymede Orbiter would concentrate on those satellites. And as I mentioned earlier, both are doing Jupiter system science, some subset of that, and a further subset is what we like to call synergistic science, the overlap region where JGO and JEO work together to make complementary and synergistic observations of the Jupiter system. We'll come back to that point in a bit. So about a dozen instruments each, and I'll talk about model payloads, but the real payloads are to be proposed by the community. So hopefully some of you will be out there proposing as part of science teams. The overall goals, again, icy world habitability and Jupiter system processes. And this idea that I really want to drive home, that the sum of these two is really greater than the parts. Having two spacecraft in the Jupiter system can do some unique science. Understanding Europa and Ganymede at the same time is going to lead to a better understanding of icy satellites in general and ocean worlds in particular. The nominal timeline is a 2020 launch for each of JEO and JGO. We envision staggered arrival in the system to aid the synergistic science, one outside the magnetosphere while the other inside Jupiter's magnetosphere. The Jovian system phases are about 2 to 3 years for each. So color-coded JEO in blue, and this is a notional timeline of one example tour where JEO makes 4 flybys of Io, several of Europa before the orbital phase, and several of Ganymede and Callisto, and then JGO making many Ganymede flybys. A resonant orbit with Callisto is the nominal plan. Many, many flybys of Callisto, and ultimately settling down first into an elliptical orbit about Ganymede, concentrating on the magnetic field of Ganymede, the internal magnetic field of Ganymede, and then a circular orbit concentrating on measuring the tides at Ganymede, doing radar sounding of Ganymede's crust. So both of these would end their prime missions in 2029 after a half to 1 year of orbital science. The Europa spacecraft is going to die from the radiation in about a year. The Ganymede spacecraft may be able to go on with an extended mission somewhat beyond that. Also, there is flexibility if either flight element is delayed or advanced. One can essentially wait in the Jupiter system, making flybys of the satellites, waiting for the other to arrive to do the coordinated observation. So there's flexibility here. The overall goal of the whole mission, soon to be named EJSM mission, is the emergence of habitable worlds around gas giants. And we think this well gets across the goals of habitability and also processes in the Jupiter system. So for the overall mission, we want to get at characteristics of the oceans, the ice shells and subsurface water, the deep internal structure, and for Ganymede, that means understanding its magnetic field, the external environments as well, the plasma environment, global surface compositions, and understanding the geology and the surface features and characterizing potential future landing sites on these bodies. So here they are to scale, the ocean worlds of our solar system. Europa is unique in its ocean being in contact with its mantle and below a relatively thin ice shell where that ocean may even contact the surface and vice versa. Whereas Ganymede is an example of a different kind of ocean, an ocean sandwich, an ocean that is deep, probably about 150 kilometers below the surface, and sandwiched between ice one above and polymorphs of ice that are denser than water below. And that is the type of ocean that Callisto and Titan presumably have. And there is the oddball Enceladus, which is a little moon that might have a sea or an ocean. And of course, our world being unusual in its ocean, being in direct contact with the atmosphere. So understanding these ocean worlds of our solar system is really going to help us understand the most common type of ocean that probably exists, not just in our solar system, but throughout the universe. And then in terms of processes within the Jupiter system, we mean the satellite system as a whole, but we also mean Jupiter itself, the magnetosphere, the magnetodisk, the interactions among the elements of the Jupiter system, and trying to get at the origin of the Jupiter system. So again, I'm going to concentrate down on Jupiter Europa Orbiter, but in parallel, most of these objectives pertain to the Ganymede Orbiter as well. These are the specific categories of science objective for the Jupiter Europa Orbiter to get at the ocean and interior, the ice shell, the chemistry and composition, geology and potential landing sites, and then Jupiter system. These are in prioritized order, and really all of them relate to the big picture question of habitability of icy worlds. Now, among the Jupiter system goals, then we can break out satellite surfaces and interiors, atmospheres, plasma and magnetospheres, the Jupiter atmosphere, and rings. And I'll step through each of these as time permits here. As I mentioned, this is a model payload, what we envision as a potential payload that could address the bulk of the science questions that we have. It's a proof of concept example, and other instrument choices presumably could be viable. It emphasizes accomplishing the Europa investigations, but it does also enable robust Jupiter system science. And the final selected payload will almost certainly be different. We've categorized these in the objective that the instruments address most, but really these are cross-cutting, addressing multiple objectives: laser altimeter, radio science, ice-penetrating radar, vis-IR imaging spectrometer, UV spectrometer, ion and neutral mass spectrometer, thermal instrument, narrow-angle camera, a medium and wide-angle camera package, magnetometer, and particle and plasma instrument. We, in scoping this out, because we literally had a TMC review, technical management and cost review, was to take a conservative approach, because these instruments will be in a very harsh radiation environment. It will not be simple to build instruments for the Europa mission, and going to the next level of complexity of instruments was not the approach that our group recommended in studying the problem. This will better get across, I think, this movie here, what Europa is going through in its daily life as it orbits around Jupiter. Not to scale, but it gives you it illustrates this tidal flexing as Europa gets closer and farther from Jupiter. Europa also nods back and forth. It librates as it orbits, and so the effect is Jupiter seems to nod back and forth in the sky if you're riding along with Europa. This illustration points out that most of the tidal heating is thought to be concentrated in the base of the ice shell, where the ice is warmest, triggering convection within that ice shell, and there may be some heat deposited within the mantle. It's a little bit of a chicken and egg problem. If the mantle is hot, then the tidal heating can keep the mantle hot. If the mantle is cold and moon-like, the mantle will continue to be cold and moon-like. So maybe there's Io down there, or maybe it's the moon down there. And that will end up being important in terms of potential habitability. Well, this is to illustrate our ocean objective, characterize the extent of the ocean and its relation to the deeper interior. And principal ways of doing that are to understand the tides and to understand the magnetic environment. In terms of the tides, we want to measure how much Europa is flexing, because if there's an ocean down there, it's going to flex 30 meters. If there is no ocean down there and we're being fooled somehow with the magnetometer data that exists, then it's going to flex just 1 meter. And the relation between the tides as measured through gravity and the tides as measured through altimetry, like with a laser altimeter, will tell us something about the structure of that ice shell. So we want to get at the gravitational tides and also the surface motion, and then stuck in the middle of those two is the magnetic environment, because again we want to study that induced magnetic field, because if we observe the magnetic field at 2 periods, unlike Galileo, which was able to observe it only occasionally on the timescale of its orbit around Jupiter, but if we observe it at the timescale of its orbit and the timescale of Jupiter's orbit, the synodic period, then the resultant induced signal, color-coded here, is slightly different at those periods. And so by measuring each, we may be able to back out uniquely the thickness of the ocean and the conductivity of the ocean if we're in a parameter space where those curves cross. So as long as Europa is being kind to us, we'll be able to get out the thickness and the salinity of that ocean. The dynamical rotation states such as obliquity can tell us about the state of the ice shell and whether it's floating. And long time scale observations of gravity and of magnetometry can start getting at whether there's topography on that rocky mantle and whether there's an induced signal that can be picked up related to the deeper interior, to the core of Europa. The ice shell objective: characterize the ice shell and any subsurface water, including heterogeneity and the nature of surface ice-ocean exchange. This objective is really critical to understanding the potential habitability of Europa's ocean, because of this issue of whether oxidants at the surface can get into that ocean. If the ice shell is thin, then all the oxidants made at the surface can literally be dumped into the ocean, in which case the ocean could be as oxygenated as Earth's oceans, due to melting and really direct interaction with that ocean. If the ice shell is thick, which actually I think it probably is, not as thick as illustrated here, but maybe 20 kilometers thick, then the interactions are indirect through convection and partial melting within the ice shell. And oxidants may have a harder time getting down to the ocean, but we need to really understand what are those processes. How does the surface communicate with the interior? And for that matter, vice versa. If there is life down in the ocean, can we see signs of it at the surface? What are the means of exchange between the surface and the ice and the ocean? And we envision doing that with ice-penetrating radar. An example here is radar sounding through an Arctic glacier, a polythermal glacier, one that's warm at the bottom and therefore has some pockets of water within the ice, which show up as scattering to the radar. So radar is able to pick out water at the base of, or within the volume of the ice toward its base here. And that's the kind of thing we want to be able to do at Europa. Imagine being able to image directly the rinds of diapirs that rise up through Europa's ice shell. Now, if the ice is warm and convecting, it's going to be a tough time to get through that ice with radar, but we would pick up the tops of diapirs, and for that matter, there may be cold downwellings where we could see deeply through the ice and potentially image all the way down to the ocean. If the ice shell is thin, then it'll be easy to image right down to the ocean, and we'll be able to tell the difference between these models using ice-penetrating radar. Of course, this has been done at Mars with ITSCAT, with MARSIS and SHARAD, and like MARSIS uses a longer wavelength and SHARAD uses a shorter wavelength to see down to the base better and to see layering better. It's envisioned that a Europa radar would have two frequencies to get at both shallow liquid water, like within the ice shell, and to try to get at the ice-ocean interface, and these issues of material exchange, and also heat flow variations by looking at the thickness of that upper cold, brittle layer. Oh, and a zoom in to some of the SHARAD data. I'm often asked the question, will we be able to tell the thickness of the ice shell? Is that an important objective here? We'll be able to tell which of these models is true, but will we be able to really get at the thickness of that ice? Well, if it's thin, yes. If it's thick, it's going to be harder. But there are multiple techniques that constrain the ice shell thickness and which will be combined. So here's a hypothetical example that Francis Nimmo helped put together here. We know so right now they're unknown to a couple orders of magnitude, the ice shell thickness and the ocean thickness. But we do know the density structure just based on Galileo, and that's constraining the total H2O layer thickness. So that's kind of where we are now. So one can imagine, once we measure the tidal deformation from the love numbers from the gravity and the altimetry, and then assuming a reasonable range of ice viscosities, or rigidities, I should say, we will have better constraints on the ice and ocean thickness. Add to that the magnetic induction that can tell us the thickness of the ocean. So here again, a hypothetical range that we might learn about from the orbiter might get at that ocean thickness, and then we've much better constrained the ice and ocean thickness. With the radar, let's say we only know a lower bound to the ice shell thickness. So in this example, Francis assumed, what did he assume, 20 kilometers here as a lower bound, because the signal dies off and we don't quite get to that ocean with the radar penetration. Well, that's all very useful information in constraining the overall ice shell thickness and ocean thickness. So we're going to use combined techniques to constrain those values. To really make a measurement, we need the radar to penetrate through the ice shell, which is possible, or we need to get a seismometer down to the surface, which is not in the baseline payload, even though the UK is studying the possibility of a simple penetrator to try to get to the surface of Europa. Moving to the geology objective, we saw a movie zooming into some of this data. Determine global, oh, I'm sorry, we're not at geology yet. We're at chemistry, but we're showing geology. Chemistry objective, determine global surface compositions in chemistry, especially as related to habitability, because understanding the composition is really key to getting at ocean habitability. So such questions as salinity, but also what is that dark red stuff on the surface of Europa? We want to understand the global surface composition in chemistry, including the organic and inorganic chemistry. So far, no organics, unless you count CO2, have been observed at Europa. But are there small patches of organics on the surface? The irradiation of the surface is going to process organics pretty quickly and rip them apart. But that's also our friend by sputtering materials up to the spacecraft. So we want to understand the radiation effects, the relationship to geological processes, and exogenic materials that come from Io onto Europa and try to separate those. And there are a few techniques, besides magnetometry, that will get at composition a little bit of the ocean in terms of salinity, at least. IR spectroscopy will help get at surface constituents of various candidate salts, have different slightly different spectral character, especially if we have fine enough spectral and spatial resolution. And INMS can measure particles sputtered up to the spacecraft. The way this synthetic INMS spectrum was generated was by looking at the likely Europa surface composition based on existing Galileo data that Brad Dalton has modeled. Taking that composition, I think a few percent organics were added, and then a simulation was done to sputter that material up to 100 kilometers. What would we see? So this is an example of a mass spectrum that we really would be able to identify the kinds of components that we suspect may be there. And then stellar occultations with the ultraviolet in orbit around Europa, we might be able to get at atmospheric composition of any active plumes if they exist at Europa. This is an example of a result of a UV occultation showing water in the Enceladus plume. If one scales Enceladus's plumes to Europa, take the same 200 kilometer high plume of Enceladus and put it on Europa, it would only be 70 kilometers high. We don't have high phase observations existing of Europa, or very few, and they're very low resolution. We really wouldn't know it if Europa today were as active as Enceladus, except looking at the torus of Europa. Actually, it was Jeff, you were involved in that as we worked that with Francis Nimmo. It says that Europa is probably not that active, but it could be something like 10% as active, if I remember right. So from orbit, one can look at UV bright stars as they set over Europa as we orbit and look for atmospheric composition in that way and potentially concentrations that might suggest activity as well. Surface features. Understand the formation of surface features, including sites of recent or current activity, and identify and characterize candidate sites for future in situ exploration. Showed that movie zooming over that 10 meter per pixel data. This is that 10 meter per pixel data. It's beautiful data, but it covers a really small fraction of Europa's surface. This mosaic put together by one of the amateurs at unmannedspaceflight.com and on the back of the new Europa University of Arizona book. So we need this kind of high-resolution coverage over lots of Europa to really sample those surface features, to map the surface at the kind of resolution in the background here, just to understand the geological relationships, the stratigraphic relationships, get at this issue of whether Europa's surface has changed through time, and also sample more of Europa's surface at 10 meters per pixel rather than the number of images we can count on our fingers and toes combined today. So we want to get the formation history, the 3D character. The topography is critical in really understanding geological processes. This issue of recent activity, potential future landing sites, and erosion and deposition, the very small scale stuff, as in this artist's rendition of that cliff and shallower slope in Connemara chaos. And here's a simulated plume that Francis Nimmo put together if you took Enceladus's plume and put it on Europa. That background image is a high phase image of Europa to show how relatively poor that data is and relatively sparse. Okay, I'm going to have to pick up the pace with the Jupiter system here a little bit, but again, we want to understand Europa in the context of the Jupiter system, and Ganymede as well in the context of the Jupiter system. So we're not going to ignore satellite surfaces and interiors, atmospheres, plasma, Jupiter itself, and the rings to understand its Jupiter's dynamic and coupled processes. IO, its tidal heat source and heat loss. Additional and longer baseline observations tell us better of IO's heat flow, the distribution of its volcanism, which is tied to its tidal processes. So to help us understand tidal heating of Europa and Ganymede, for that matter, observing IO helps constrain those processes. It really is the tidal engine of the Laplace resonance. In fact, Europa's orbit is tied to IO's and its heating cycles, and we think Europa might become more and less active through time, and may even be in a waning cycle of activity now, as tied to Europa, perhaps on a 100 million year time scale. Ganymede and Callisto, again, JGO is going to focus more on these, but from the JEO perspective, we can help get at water in Ganymede and Callisto through improved and additional magnetometry measurements. They're pretty good measurements at Callisto that suggest a subsurface conductive layer. At Ganymede, it's tougher to tease that out of the Galileo data because of the intrinsic magnetic field of Ganymede. We want to better get at Ganymede's surface materials, Callisto's surface materials, and the internal evolution tectonics of these bodies. Imagine taking a radar to the grooved terrain of Ganymede, and it's not going to penetrate that deep, but it may penetrate deep enough for us to understand, are there layers in there that tell of past cryovolcanism, or is it tectonism alone that shapes Ganymede's grooved terrain? Can we penetrate down through some of this surface material at Callisto to better understand its bed ice, if you like? The satellite atmospheres, the composition, the variability, the dynamics of the atmospheres of all three of the inner three Galilean satellites, how they vary with location in the plasma sheet. We know little of Europa's atmosphere from our Earth-based observations alone. The plasma magnetosphere environment of Jupiter, escaping neutrals, the Io-plasma torus, pickup and exchange processes, satellite interactions, of course, including with Ganymede's magnetic field. This is the only place in the solar system we can go to study an analog of the Earth and Sun magnetospheres is by studying the Ganymede-Jupiter magnetospheric interactions. A lot of potential for improved plasma magnetospheric science there. Jupiter's atmosphere, especially dynamics. Of course, one of the biggest losses for Galileo in not having its high-gain antenna was that it was not able to take movies, long-term observations of Jupiter and really get at the atmospheric dynamics. So we'll have a baseline of 2.5 years with which to watch Jupiter with every periapse passage. So atmospheric dynamics and circulation, atmospheric composition and chemistry, atmospheric vertical structure. Although the model Payload does not have a Jupiter dedicated instrument, the existing instruments can do pretty good science at Jupiter, and it's possible that someone will propose and the mission might fly a Jupiter dedicated instrument. The JGEO spacecraft in its model payload does have a sub-millimeter wave instrument which would do really groundbreaking science at Jupiter. The rings, understanding the source bodies, the dynamical processes, comparing Jupiter's tenuous and dusty ring to the other ring systems of the solar system will really help us get at comparative studies of ring dynamics and evolution. So again, really rich and robust science of Europa and the Jupiter system. A couple of specifics on the Envision mission. It would launch on Atlas 551, powered by 5 MMRTG. Actually, I should take off the ASRG. It looks like that's off the table for this mission. We mentioned the mission timeline here, but I'll mention in particular the final disposition is Europa Impact. So what that means is you do, at the end, the spacecraft does crash onto Europa, and for planetary protection purposes, we cannot pollute Europa's ocean in the interest of future exploration of Europa. So that means components that have not received a lethal dose of radiation because they're on the outside of the spacecraft, exposed to the magnetospheric environment, will have to be sterilized in some way. And so that is a severe constraint on the instruments. So they have to deal with the radiation environment, and they have to be thoroughly sterilized before they can fly, heat sterilized or other processes. Radiation that the spacecraft experiences is nearly 3 megarad behind 100 mils of aluminum. The plan is to use a combination of rad-hard parts and tailored component shielding. This is different than the Juno approach, which really concentrates on shielding and using a vault. We're above the level of radiation where that's a feasible approach. So the approach is to use parts that are rad-hard. If you have a 1 megarad hard part and put it behind shielding, then there's no problem in dealing with the level of radiation. But this will imply different approaches than typical instruments. Instruments will have to go back to the drawing boards, and so we in the project understand that. We need the instrument proposers to understand that. If you intend to propose, there's one more instrument workshop that's coming up. There have been a few this summer, last week in July, in the Pasadena area, and there will be discussion of planetary protection, of the radiation issues, and probably of the AO itself, which is due out on the order of 1 year from now. Those who've worked Cassini understand the problem of not having a scan platform. While Europa does not have a scan platform and its instruments are nadir pointed, the antenna is steerable, and so it communicates always with Earth as the instruments look downward. And so there's actually little onboard memory because most of the data is fed back essentially as it's collected. And the instruments operate together in making their observations. So this is just a notional plan of the Europa science campaigns where we would start at a high altitude, say 200 kilometers, get the global context, understand the gravity field, within a couple of weeks know if there's an ocean there from the tidal deformation, and then go down into a lower altitude orbit, rinse and repeat, and now have twice the resolution, take longer to obtain global coverage, color, stereo, radar profiling. And after 100 days, here's the density of profiles at the equator. So that's the density the laser altimeter will see because it's envisioned as on all the time. Half of this density, a quarter of this density for, say, a thermal instrument or an IR spectrometer in profiling mode, a quarter of that density because half the time it's night, and we are envisioning an even odd orbit ops scenario where the even orbits emphasize the optical remote sensing, the odd orbits emphasize radar sounding to locate water, and that helps with the power constraints and with the data rate constraints. So that's our going in plan at least. And then targets, in addition to all the profiling observations and global synoptic observations, targets that are coordinated and really use the power of all the remote sensing instruments at once, along with a radar profile through it, and the number of such observations increasing with time. So this third campaign is envisioned as emphasizing these coordinated, targeted observations. And let's see, I forget, I think we get 800 or so of those coordinated, targeted observations, each about 250 megabits over the first 100 days. So this emphasizes the first 100 days, where the science definition team said, in the first 100 days, we want to be able to accomplish all of the critical hypothesis testing so that in the rest of the mission, we can follow up on discoveries. And also, because of the radiation environment, we want to be sure to get the highest priority science done as quickly as we can, and then breathe a little easier through the rest of the mission. Right, this is showing these coordinated targeted observations again, and a zoom in of the profiles after 100 days. After 9 months of mission, there are about 1,700 of these coordinated targeted observations where, well, this is the WAC, that's going to cover everything globally, and this is the medium angle camera, which is about 10 meters per pixel, that, like those Connemara, those few Connemara images that we saw earlier. Narrow angle camera, 1 meter per pixel down the center, infrared imaging spot. If the UVIS is an imager, the ultraviolet instrument is an imager, it would be coordinated as well. And the ice-penetrating radar doing a low data rate profile, laser altimeter, and the thermal instrument always on. And I should mention the previous slide set up there somewhere that the MAG, the particle and plasma instrument, are envisioned as always on, and the INMS as 50% duty cycle. Again, we had to show proof of concept that this would work, even though we don't know these are the instruments that would fly. And just simply say that in campaign 4, the rest of the mission, there are many things that one could envision doing, and ultimately the PSG will get its heads together and say, how should we plan to spend that time? For example, dipping down low to get higher resolution data or to see what the INMS can see. In terms of Jupiter system science, every perijove, it's envisioned that something like 25 gigabits will be collected. There's 3.2 terabits available during the total Jovian tour. That's about 1,000 times the Galileo data return, and it's on par with Cassini-like data rates. Maybe it's too much detail, but 33 perijoves, each of which Jupiter system science, Jupiter observations can be done. There are lots of flybys of the satellites. 3 IO for science, 1 additional one to get into Jupiter orbit, 6 Europa, 6 Ganymede, 9 Callisto, each of them getting exciting new science on the surfaces of those satellites. This is an illustration of one of the IO flybys. It's not clear that NASA would ever let us go through a plume, but wouldn't it be exciting to be able to send an INMS through one of IO's plumes? As Torrance Johnson reminds us, Galileo did fly through a plume at 200 kilometers. We learned after the fact, and so maybe we can convince others that this will indeed be safe. And you notice the instrument deck had to rotate and keep up with the satellite as we flew by. Examples of IO resolution from Europa's distance, about 2.5 kilometers per pixel on the anti-Jovian side, 10 kilometers per pixel on the sub-Jovian side with the narrow angle camera, and with the medium angle camera about 25 kilometers per pixel on the anti-Jovian side. So a lot of exciting I/O science and monitoring to do as well. And I'm going to hurry through the JGEO perspective, but again, it mostly parallels what we've seen in JEO. The key science phases being the Jupiter system, the Callisto, resident orbit, many flybys of Callisto, and then Ganymede, elliptical orbit, and then a circular orbit of Ganymede. Similar objectives, but adding in Ganymede's unique internal intrinsic magnetic field. The envisioned payload is very similar with the addition of a sub-millimeter instrument and a radio and plasma wave instrument on JGEO. Let me skip those and go right to the synergistic science slide. So we looked at the timeline earlier, and we mentioned an example of the kinds of science that's unique to two spacecraft, and that is, well, as Galileo and Cassini briefly did, one spacecraft can be, the arrival at Jupiter can be staggered. So one spacecraft can be in the Jupiter magnetospheric environment while the other is outside monitoring the solar wind, and we can learn the effects, direct effects of the solar wind variations on the Jovian magnetospheric environment. And again, that's been done slightly by Galileo, and we'd have a chance to do it again with additional instruments. But also imagine we have the opportunity to fly by I/O and potentially even measure plume composition, but certainly observe active volcanism in situ, close up. And at the same time, from a distance, the other spacecraft, JGEO, is observing the Io Taurus and the effects of volcanism on the torus, helping us really trace particles and their histories and how volcanism helps light up the Io Taurus. During the bulk of the Jovian tour, we can do what we're loosely calling stereo. That is, we can observe Jupiter at two emission angles at the same time to better characterize its atmosphere. One might be observing the night side and one the day side at the same time. We can literally do stereo at Io, seeing plumes in 3 dimensions. There's a wonderful opportunity that we're investigating of dual spacecraft radio science. If you think about the geometry of radio occultations, if we're viewing from Earth and a spacecraft goes behind Jupiter, then we're the spacecraft is always going behind Jupiter and along the terminators or near the terminators as viewed from Earth. But if one spacecraft is disappearing behind Jupiter as viewed from another, the geometry can be such that the occultation takes place along any longitude of Jupiter. And not only that, the signal to noise is 3 orders of magnitude better from spacecraft to spacecraft than it is from spacecraft to Earth. So this is a unique opportunity, and we're looking to ensure that the spacecraft can talk to each other in order to take advantage of this. And for satellite ionospheres, this is also fantastic science. A very exciting prospect is if JGEO, Ganymede Orbiter, goes into orbit around Ganymede while the Europa spacecraft is still making flybys of Ganymede and still in the Jovian tour, then JGEO can be monitoring the effects of Jupiter's magnetic variations on Ganymede. So analogous to the outside-inside the solar wind experiment, we can be measuring Jupiter's magnetic field and looking at the effects on Ganymede's magnetic field. At the same time, this helps in teasing out the intrinsic magnetic field of Ganymede by monitoring Jupiter's magnetic field. So those are examples of spacecraft synergies. You might think of others. In fact, there's going to be a special session at the Europlanet meeting, the EPSC, in September in Rome, which will invite contributions on potential synergies of two spacecraft in the Jovian system. We need to think about ring occultations and whether the spacecraft-to-spacecraft communication will be able to get at the, do successful occultations of that tenuous Jupiter ring. So for more information, please check out the website, APFM, which is for Outer Planets Flagship mission.jpl.nasa.gov. And once we have a mission name, hopefully we'll have a better mission website address. I mentioned the workshop that occurs this summer. And again, it's Kurt Niebuhr has stated, our NASA contact has stated that about a year from now, early next year, an AO is due to hit the streets asking for instrument proposals. So I hope that some of you will be involved. Thanks very much. I'll take a few questions.
Hi, Bob. This looks like a wonderful mission. I do notice it's a great deal of time in the future, and I'm wondering if there's a viable direct ascent mission. It looks like you're looping around the inner solar system a lot because it takes you 8 years to get there. What are the prospects for a direct mission?
Well, a little less than 6 years to get to the Jupiter system, and then, yeah, we got 2.5 years to get down to Europa. And the faster you get there, the less total radiation dose you have. We've looked carefully at the trades. The technical folks at JPL have looked carefully at the trades. And you deliver a lot more mass by spending more time, right, in the inner solar system doing the gravity assists. So we think the trade is worthwhile to get more mass into your payload and to have more mass reserves at this point in the mission design. In fact, the decision to go by IO is a technical trade. That's so that we can get more mass into the system, as opposed to the science trade. The scientists were more reticent to go by IO than the technical team was because of the added early radiation hit, but it's not so much compared to the whole radiation dose.
Do you have an Earth flyby in plan now?
Yes, it's a Vega trajectory, so Venus, Earth, Earth.
Jeff Cussey's volunteered to be the PAO.
Have you gone through that before? Okay.
So my recollection is that one of the satellites, it may have been Io, there were not only plumes but intense lightning storms. Can you comment on that? And if so, what the implications are for any habitability?
I don't know of any lightning at Io. Maybe you just mean the plasma environment, but no lightning at Io. There is lightning observed at Jupiter, in the atmosphere of Jupiter itself. Yeah, and there's been speculation about life in Jupiter, but not so much that we couldn't dispose of the Galileo spacecraft into Jupiter.
Hi, Bob. Great talk. As you know, in Italy, the Russians were talking about a coordinated lander mission on Europa based on the Phobos lander. Has there been any discussion between JPL and EKI about that? And do you have any insight into the plausibility of that idea?
There has been some discussion. There was a meeting at EKI about a year ago, although I wasn't able to attend, others were able to go. The timing is such that it would be a follow-on, that coordinating them doesn't seem feasible. But Russia does seem to be interested in the possibility of Europa lander and of the Europa Orbiter being a scout for potential landing sites. So it's hard to judge how real it is in terms of the monetary cost of such a mission, but the prospect is exciting. We're encouraging of the prospect. I mean, they've been to the surface of Venus. They can put together a robust mission, but a lander is not simple in terms of getting enough propellant into orbit to slow you down enough to get to the surface, and that's a lot of the challenge that we've seen in looking at the potential for a surface package.
Bob, a couple of things have changed in the year or so since the last technical study. One of them is that, speaking of plutonium, is that the Russians seem not to be willing currently to sell us the plutonium we need. And so what would strike me is, I don't think we have enough plutonium to send 5 MMRTGs. You can correct me on that. But it would be unwise from a negotiating standpoint to take ASRGs off the table until such time as you have plutonium in hand. The other thing that's changed is Mr. Obama has changed the manned spaceflight program so that now there will be commercial availability of man-rated heavy-duty rockets. The reason why Europa study went for radiation-hard parts is that they were unwilling to spend the money required to buy heavy-duty rockets because the rocket manufacturers didn't want to launch plutonium. Now, that's my understanding of that. If heavy-duty rockets become available, is the mission willing to reevaluate a very rad-hard vault versus a rad-hard parts?
All right, let's see if I can address the parts of your question that I can. So let's start with the latter part. Moving to Delta IV Heavy is not going to fix our problems in getting us there a lot faster. We would still, I believe, the trade would still be a Vega. And others could answer that question better than I, but that trade's been considered because the Delta IV Heavy was the default launch vehicle until we scrubbed and said, you know, we can fit on an Atlas and we can save that 400 million or so that it would cost. If there is some super duper heavy launch vehicle, there might be the potential to use it, but of course we'd want to know it exists and would be ready in time. And that goes to the ASRGs as well. They don't exist. They're not rad hard. It's not clear what the vibrations would do to your gravity measurements. And although there's talk of testing an ASRG on a discovery mission, we don't want to test it on a flagship mission. So it's very unlikely that it would be ready and proven in time for this mission.
I understand you want to use that.
Right. NASA seems more secure in the availability of plutonium than I am. As you know, there is an agreement now to restart manufacture of plutonium. That's in the budget, at least, for us to restart.
It was pulled out during the last budget.
But as far as I know, it's in the next year's budget. Correct me. Yes, it's in the upcoming budget. So. But again, NASA seems confident in this and has directed us that MMRTG is the probable way that this mission will go. You're right. I shouldn't say for certain, but that's the default plan.
Your negotiating position with the Russians is much better if they know you have an option.
That there's an option. It's not clear from the.
Force you to take a lander. I know. Push me, stretch my arm.
Again, it's not clear to me from the conservative standpoint of designing a conservative mission that we know will work, that we'd want to go with ASRGs. But you're right, they're not fully off the table.
Going back from politics to science, you mentioned the role of oxidants in the ocean and that they would be generated at the surface through UV irradiation and then be transported down. We do have some experimental evidence and that actually when rocks are flexed or stressed, they do produce electronic charges that oxidize the water to hydrogen peroxide at the water-rock interface. So there might be a source of oxidation right at the bottom of the ocean.
Interesting, as if that could be a significant amount. Should mention serpentinization of the rock is another potential
for this you need
source of
higher
energy.
Temperatures. Right.
Right. If there's activity down there, especially. So that's it. And one more source is radioactive decay of potassium within the ocean and ice shell. Now those are a lot lower levels than we're talking about at the surface. So that's why for for habitability, it would sure be nice if the surface is in contact with the ocean. If it's not, there are still other means to supply chemical energy to the ocean, but it's not as promising, not as high in energy.
Two questions about the instruments on the Europa orbiter. Do you expect that the spectrometer will have the sensitivity and the spatial resolution to get down into those grooved crack areas and actually resolve any complex organics? And secondly, over the course of the mission, with the high-resolution cameras taking images of a large portion of the moon, do you expect that you might see movement of ice over the long period of time?
But let's go to the spectroscopy part first. Again, the model payload, this is just a concept, had an IR spectrometer with, I believe, 25 meter per pixel on it. I can't remember if we might have gone to 50 there at the end, but I think it had 25 meter per pixel. The widths of the central trough of ridges are something like 200 meters wide, so you'd just be able to resolve that. That was some of the justification. Spectral resolution, again, is going to be up to the proposer. I think we had in there 6 nanometers for the shorter wavelength and 10 or 12 for the longer wavelength. So that's pretty good. And if you try to get better, it's possible, but you drive up the cost and mass of your instrument, and then you start getting into data rate issues as well. So I think the answer is yes, and that was part of the plan for that. In terms of imaging, well, one of the experts in that is here at SETI, Cynthia Phillips, in terms of looking for changes on Europa, but so far Cynthia is limited to Galileo Voyager and very few Galileo comparisons. So the most promising way to find changes, if changes are slow, as I suspect they are, is comparing Galileo imagery to the Europa orbiter imagery at high resolution, those few high-res areas, and seeing if there are any changes there. It's conceivable to see changes on the course of the mission while in orbit, but I wouldn't bet on it. But I'm sure that'll be an important area of investigation of whether there are changes. In terms of the tidal deformation, I don't think we have the resolution to literally see things move on the tidal time scale. They might move 10 or maybe tens of centimeters. I suppose it's not out of the question if you had a good enough imager, but it's not clear to me you'd really see those changes. But again, I'm sure we'll look.
Bob?
Oh.
Yeah. I guess I'm back to the science. Following kind of what Friedman was talking about, you didn't really get much into it as far as the implications of the tidal heating of the rock. So I'm just curious, if you can remind me what the argument is about why there wouldn't necessarily be any, and is the implication that if you do find that's the case, that the resonance is in fact ancient? Is that the argument, that it's been experienced for so long that even
possibly. So the argument is if you have something warm and squishy, it can tidally heat and stay warm and squishy. If it's cold and rigid, then it doesn't deform enough to tidally heat. So you need the mantle to stay warm and squishy. And if you ask Bill Moore, who's thought about this problem, he says the interior is either moon-like or Io-like. In reality, and those are the steady states, and that there's an unstable equilibrium between, but he doesn't think it's there because it's unstable. So either moon or Io, in terms of how Europa would get the heat out of its mantle. In reality, the eccentricity of Europa may change on this 100 million year timescale as pulled by Io, related to its tidal heating and conservation of its angular momentum. And so, when pushed at it, this problem hasn't been modeled, but at least I was able to talk to Bill Moore about this, who thinks that, yeah, if it's heating and cooling on 100 million year timescales, maybe it never gets to the steady state, cold or hot. So maybe Europa's interior is moving say, from hot toward cold, but then it heats up again and it swings back. So maybe it never makes it to an equilibrium state. And that's my gut feeling for what might be going on, but it hasn't actually been modeled. So maybe you could have a lukewarm mantle. And the significance is the comparison to black smokers on Earth and extreme environments there, and the reductants, the chemistry that pours out of black smokers on Earth where water contacts hot rock. And that's the kind of environment, especially if there are oxidants from the surface, that might be able to support life.
Okay, if there are, I had one question actually.
Okay.
So the relation of the scale of the ridges on Europa, are they thought by modelling to scale with activity, with heat, plumes that are nearby, or is there what's the control on the scale? Because there seems to be quite a range of scale.
Yeah, there are. We don't know the cause, but we do know when you look at the stratigraphy where we can make out, the older ones, older being maybe only 100 million years old, as far back in the stratigraphy as we can see, the older ones are wider, suggesting that the icy shell may have been more mobile back then. And it seems that there are fewer and narrower ridges more recently in the stratigraphy. So that is consistent with an idea that Europa's shell has thickened up and stiffened up. Also, the chaotic terrain, the model terrain, in general, is younger than the ridge terrain. And if the model terrain's from convection, that's consistent with the ice shell thickening up to the point where it started convecting. So those are the geological arguments that point to maybe Europa is in a cooling phase. And that's consistent with the thought that Io might be in a cooling phase. So, so maybe its orbit is circularizing a little bit, it's cooling off a little bit, and the other end-member extreme is Enceladus, where it's, potentially today in a very active phase, and it's gonna cool off soon. But at Enceladus, it may have very short bursts of extreme activity, whereas Europa might be more gently wandering between active and less active phases.
If there are no further questions, then as a memento of your visit, we have a special SETI pin. Limited edition.
Oh, fantastic.
SETI pin.
Thank you very much.
So if you'll all join me in thanking Bob.
Thanks so much. Excellent.
Next week will be another icy topic as well. So.